All right. So my name is Mehrnoosh Tahani. I'm a Banting sponsored by the Government of Canada and a KIPAC Fellow at Stanford University. This month, I am also a JSPS Fellow at Nagoya University. So I'm presenting Chapter 6, Magnetic Fields in Star Formation from Clouds to Cores on behalf of Kate Pattle, Laura Fissel, Tia Liu, and Eva Ntormousi. So Kate will also discuss the magnetic fields of cores, and she is a Royal Society Fellow at University College London. All right. So we know that the interstellar medium is magnetic, and magnetic fields influence the formation of stars, from formation of clouds, stars, and ultimately planets. And they influence the evolution of the galaxy through this process. We've made significant progress since the last protostar and planet meeting, and there has been many observations, for example, by Planck, James Clerk Maxwell Telescope, SOFIA, ALMA, VLA, LOFAR, and others. For example, here I'm showing the Planck observations that they observed the plane of sky magnetic field, as you can see with the drapery lines here. So all these observations have shown us that we cannot afford to ignore magnetic fields anymore. So in this chapter, we start by talking about magnetic fields of clouds, and then we get into the substructures and filaments within the clouds, and then we talk about magnetic fields of cores. And when we talk about magnetic fields of these structures, we have three main questions in mind. So one question is how the magnetic field morphology of these regions look like, and how do their 3D magnetic field morphology looks like. Then the second question is, what's the role of magnetic field in directing the gas in these regions, and influencing the star formation process? And the last question is, how do the energies in all these systems compare to each other? So for this purpose, we need to look at the techniques of observing magnetic fields and define metrics to characterize the magnetic fields in these systems. So let's start by looking at the observing techniques of magnetic fields. We've discussed several techniques in our chapter, and in the mini talk that is still available on Mattermost, we've mentioned some of these techniques. Here we focused only on three main techniques. So Zeeman splitting provides the line of sight component of magnetic field in the interstellar medium, and is the most accurate technique and direct measurement of magnetic fields. And it has been used both in molecular and diffuse ISM, or atomic ISM. However, Zeeman measurements require strong magnetic field and long telescope integration hours, so there are not enough Zeeman measurements per star-forming regions available. Faraday rotation is another technique that provides the line-of-sight component of magnetic fields. When a linearly polarized electromagnetic wave passes through a region that is magnetized and has free electrons, a magneto-ionic medium, its plane of polarization rotates, and the amount of rotation is proportional to wavelength squared and magnetic field and free electron volume density. Three main techniques can be used to use Faraday rotation to determine magnetic fields in interstellar regions. So one is the classical technique of using point sources, for example, extragalactic sources, quasars, or pulsars, and using the linear relation between lambda squared and delta psi. And this has been widely used to provide the magnetic field in large-scale galactic magnetic fields or magnetic fields of highly ionized regions. Rotation measure synthesis is another technique that can provide the magnetic field in diffuse regions. And it's based on the diffuse emission from synchrotron radiation. And it actually decomposes the polarized intensity based on the amount of Faraday rotation that the electromagnetic wave experiences along the line of sight. For molecular clouds, the technique of Tahani et al. 2018 can be used, where they use an on-off approach and point sources to determine or decouple the rotation measure of molecular cloud from the rotation measure of everything along the line of sight. I have a poster that briefly discusses this, so if you're interested, please let me know and stop by my poster. So dust polarization provides the plane of sky component of magnetic field. And it's based on the alignment of elongated interstellar dust particles, their main axis perpendicular to magnetic fields. And this alignment, the leading theory that can explain this alignment is radiative alignment torques. And it has been used to observe magnetic fields in both diffuse and molecular regions. And we can also use dust emission in far infrared and submillimeter or dust extinction in near infrared and optical observations. So now that we've talked about observing techniques, let's talk about the metrics that we can use to characterize magnetic fields in the regions of the interest that we are studying. And particularly, we want to see how we can compare the energies in the system compared to the energies of magnetic field. So the magnetic energy itself is proportional to field squared. Plasma beta enables us to compare thermal pressure to magnetic pressure. A value less than 1 means that the system is magnetically dominated. Mass to flux ratio is a metric that enables us to compare the gravitational energy to magnetic energy, and is proportional to column density, to the ratio of column density to magnetic field. A value less than 1 means that the system is magnetically dominated and magnetic fields win. A value more than 1 means that the system is magnetically supercritical and gravity dominates. Alpha and Mach number enables us to compare turbulent to magnetic energy. And a value less than 1 means that the system is subalphanic and magnetic fields win the game. A value more than 1 means that the system is superalphanic. Another relation is the relation between density and magnetic fields that have been seen in observations and in simulations. This relation is quite important, and we'll keep coming back to it in this talk. This relation was first observed by Crutcher et al. That they used Zeeman measurements, as you can see with the green points here. And what it says is that the density and magnetic field have a power law relation beyond a density threshold, and it's constant below it. So where this transition from constant to power law happens is quite interesting and important in our studies of magnetic fields and interstellar medium. So in all these metrics, we need to find the strength of magnetic fields. So one of the widely used techniques that have been used to determine the strength of magnetic field, particularly the plane of sky magnetic field, has been the Davis-Chandrasekhar Fermi or DCF technique. And it relates the strength of plane of sky magnetic field to the square root of density, the non-thermal line width, assuming that they're probing or tracing turbulent motion from alpha wave, and we use gas tracers that trace the same material as dust, and dispersion in polarization angle. So the original form of DCF has Q equal to 1, which actually overestimates the magnetic fields. Q, and because of this overestimation, there has been different approaches and different models and studies trying to modify this equation further. So for example, in the classical approach of DCF, Q equal to 0.5 has been proposed to account for this overestimation, as well as the use of more complex analysis, such as the use of structure function analysis. So one thing is that DCF, since it was first introduced in 1950s, has been very controversial, but at the same time widely used. So to look into this a bit further, we compiled all the DCF measurements available from the publication of Ostreicher et al. 2001, Pattle et al. And Heitch et al. 2001. And compared our compile of DCF measurement, as you can see with the black dots here, to the power law relation that they mentioned, as you can see with the dashed red line. And the Zeeman measurements are shown in blue. We see that the compile of DCF actually, even though it's slightly overestimating the magnetic fields compared to Zeeman measurements, it follows the same trend as the power law relation and as the Zeeman measurements. And that's up to the densities of 10 to 7, where we are getting interferometric data and for high density regions. And since DCF is actually a measure of alpha and Mach number, we compared or looked at the alpha velocity and alpha Mach number as a function of density as well. And we see that alpha Mach number is actually constant, almost constant, and subalphanic. The system is subalphanic up to densities of 10 to 7, which is consistent with the DCF assumption. The subalphanic is consistent with the DCF assumption. We can also quantify the geometry of magnetic fields. And for this purpose, histogram of relative orientations have been used. Using HRO, observations have shown that in cloud scales, magnetic fields tend to be perpendicular to filamentary clouds, and they tend to be parallel in high density regions, and they tend to be parallel to it in low density regions. For example, here I'm showing the VII molecular cloud as observed by Fissel et al. 2016 using BLASTPOL, and the magnetic fields in high density regions are clearly perpendicular to it. So HRO investigates the orientation between density gradients and magnetic fields and examines this alignment or alignment in density beams, column density beams. And it was first used and introduced in Solar et al. 2013 and has since been used in various studies and modified further. Zhou et al. Explains this study of alignment based on the alignment of cows with respect to the magnetic field of the Earth, and it's quite fun to read. So based on the HRO analysis to quantify this further, we can use HRO parameters. For example, Zhou et al. Uses the HRO parameter of projected Rayleigh statistic when parallel positive values indicate parallel magnetic field to density structures and negative value indicate perpendicular magnetic field to the structures. For example, Zhou et al. They looked at VII molecular cloud, and using this ZX value, they quantified the alignment of magnetic field better with the region of the VII, looking at the transition from parallel to perpendicular magnetic field. This transition from parallel to perpendicular by Crutcher and Campbell 2019 has been shown that there is a relation between where this transition happens to where there is a break in the power law relation, the power law that we talked about before. So this transition may indicate that there are so I have it here, there are convergent velocity flows and may have a relation between the densities or metrics of the magnetic field. So to investigate this further, we looked at the simulations that study or use HRO to look at the transition from parallel to perpendicular. We compiled the studies from these simulations, looked at the density at which this transition happens as a function of alpha and Mach number. And we do not see a particular trend between the two. However, this is not conclusive. And that's because of the limited available simulations and differences in how different groups use alpha and Mach number. Seyfried et al. 2020 as well highlights the importance of viewing angle. So if we have a magnetic field and a density structure that are perpendicular to each other in 3D, when projected onto the plane of the sky, they can actually look parallel to each other. So to look into the 3D magnetic field morphologies, let's start by cloud scales. So for 3D magnetic fields, we need plane of sky magnetic field observations and line of sight magnetic field observations. Both line of sight and plane of sky magnetic fields in the scales of cloud have been shown to be somewhat coherent and have an almost ordered component that we can associate with magnetic fields. For example, here I'm showing the line of sight and plane of sky magnetic fields of Orion A. Points that are blue, they're magnetic fields toward you, red are magnetic fields away from you, and there seem to be a coherent structure. And the Planck magnetic field observations seem to be mostly perpendicular to the region. Now, using these line of sight and plane of sky magnetic field observation, and the morphology that was proposed for Orion A is the arc-shaped morphology where the magnetic fields bend around the filamentary structure. And this is just a bend, it's not a complete toroidal. Now, further studies were able to reconstruct the complete 3D magnetic field of this ordered large-scale component, and they were able to identify the orientation and direction of this arc. Now, studies were also able to propose a scenario for the formation of the magnetic field in this region, which this scenario may actually hint to the formation of the cloud itself. So now that begs the question, what are some of the astrophysical insights that we can begin to gain? Yeah, okay, thanks. What are some of the astrophysical insights that we can begin to gain from these observations and comparing with, for example, like formation of the magnetic field in these regions. For example, the astrophysical insights from cloud formation. There are 4 main cloud formation scenarios discussed in our chapter. For example, formation from gravitational instability of the galactic disk, where the magnetic fields become buoyant, and they actually result in a large-scale bending of magnetic fields. Also, the zoom-in simulations from kiloparsec to molecular clouds also enable us to look at the condensations or formation of the clouds as the result of condensations from large-scale turbulence. And we also have cloud formation as the result of colliding flows. And a specific case of colliding flows is shell expansion and interaction, for example, simulated by Ntormousi et al. 2017, where compressions from H2 bubbles or supernovae can result in the formation of molecular cloud. Now, model of Inutsuka et al. 2015 showed that multiple compressions are needed to actually form molecular clouds. Although there has been a few studies that find their magnetic field observations consistent with the model of Inutsuka et al. 2015, these are very limited number of clouds, and they're all nearby clouds. So we need many more observations, particularly magnetic field observations and robust predictions from cloud formation models regarding the magnetic fields, so we can compare with the observations. Now, moving to smaller structures, let's look at the NGC 6334 molecular cloud. This is a massive star-forming cloud and is in the galactic disk and is nearby. And the large-scale ordered component of magnetic field are perpendicular to it and actually hinder the star formation process and the gravitational collapse in the region. However, there are structures in the region where we see that magnetic fields are clearly influenced by the evolution of the cloud. For example, there are a number of H2 regions here. One of them you can see with the orange bubble here, where the magnetic fields are pushed and oriented tangential to the boundaries of the H2 bubbles. There are also filaments or subfilaments within the cloud where they're merging to the main ridge, and the magnetic field actually transitions from perpendicular back to parallel at the location where the filaments are merging to the main ridge. In the very high density region, there are also linear or hourglass morphology observed as well. So, what are the observations in the filament scales telling us? So, filaments within these clouds. Statistically, we see that the magnetic fields tend to be, again, similar to cloud scales when we look at the envelopes of filaments, parallel or perpendicular to these filaments. And this alignment may actually depend on volume density or the contrast in column density. For massive filaments, other than the perpendicular and parallel magnetic fields, we see a transition back to parallel. And this transition back to parallel is happening, based on the limited observations that are available, is happening for very high density filaments or for regions that the filaments are merging into a hub system, or as we saw with the main ridge of the NGC 6334. For example, here we see a massive filament observed by Liu et al. 2018, where the magnetic fields are perpendicular to the filament, and at the edges or the ends of the filaments, they transition back to parallel. So a horseshoe, a double horseshoe magnetic field morphology has been observed in the OMC one as well, or a pinch magnetic field morphology has been observed in simulations, for example, by Gomez et al. 2018, as you can see here. So these magnetic fields actually may stabilize the filament against gravity. And that actually may depend on the morphology or geometry of magnetic field with respect to the filament. So a parallel or perpendicular magnetic field may stabilize the filament and hinder the fragmentation of the filament. And toroidal magnetic fields, if they exist, they can actually squeeze the filament further and work together with gravity. And based on these geometries, different fragmentation modes, for example, aligned or clustered fragmentation, have been proposed. And in all these filaments, or like in these scales, magnetic fields can influence the star formation process. There hasn't been any observations, or there seem to be little or no role of magnetic field in setting the initial mass function, and they actually may reduce or can reduce the star formation efficiency. For the star formation rate, even though that the theory suggests that they should, as a result of magnetic field, star formation rate should be reduced, the observations are inconsistent. For example, observations by Lee et al. 2017 showed that there is a relation between orientation of magnetic field and the star formation rate, and Solar 2019 actually showed that there is no real orientation. Now, moving on to cores, Kate will talk about the magnetic fields of the cores.
Thank you very much. Yes, I've been deputized to give a quick overview of the role of magnetic fields in core evolution. So when I say core, I mean any object that's roughly spheroidal and likely to go on, if it's gravitationally bound, to form an individual star or an individual stellar system. Naturally, the definitions get a little hazier at higher masses. And in a way, we're in luck here, because this is one of the few parts of the magnetic field world where we have a very solid prediction from theory about what we expect, which is that if a magnetic field is sufficiently strong, when gravity eventually overcomes it, you will develop what we call an hourglass morphology. What happens here is essentially the flux freezing assumption breaks down, which we've been relying on up until this point. The neutrals start to drift in, decoupling from the magnetic field. The core becomes gravitationally unstable, and as the entire thing collapses, the magnetic field and the ions get dragged in together as well. So this hourglass morphology gives us a very nice indication of a magnetic field that used to be dynamically important. This happens when the amber-polar diffusion timescale gets short. The amber-polar shorten the freefall time. The amber-polar diffusion timescale depends on the length scale and the density and the cosmic ray ionization rate. So it makes sense. It's only in these particularly small, dense and embedded things that it can get short enough for this to happen. So that's the theory. Do we see it in practice? The answer is sometimes. Interferometric observations of protostellar cores, so cores that already have stars formed within them, in some cases do show this hourglass geometry. Famously, the NGC 1333 IRAS-4A low-mass protostar, but also here we've got a massive cluster-forming core, G240.31, that also shows this characteristic geometry. But that's in some of the objects that already have formed stars. If we take one step back to starless or pre-stellar cores that haven't yet formed any central hydrostatic object, the observations get somewhat more ambiguous. we fairly consistently see linear, well-ordered magnetic fields in these dense cores, often broadly perpendicular to the major axis of the core, which is suggestive of a dynamically relatively important magnetic field. But it's hard to say with any certainty that we've yet observed hourglasses on pre-stellar size scales. So, in the absence of our nice, clean geometric pattern, what else can we use? One option is look at the magnetic field strength. So Myers and Basu, a couple of years ago, compiled essentially all of the observations of pre-stellar and protostellar cores and found that the magnetic field strength goes as density to the 2/3, which is precisely the prediction for a weak magnetic field. So can we from this conclude that magnetic fields are in fact dynamically irrelevant and the thing's just collapsing homologously? It's never going to be that simple. The authors here argue that essentially because of the various scalings involved over a narrow mass range, if your objects are near virial stability, you'll inevitably recover this n to the 2/3 relation regardless of the actual state of the thing. So, our other option is to go back to the idea of seeing whether these things are collapsing on a free-fall time or evolving on something more like the amber-polar diffusion timescale, for which we need to know the lifetime of a starless core. There's two ways of doing this, one of which is through number counts. Typically, you just count your pre-stellar cores, count your class 2 protostars, which are evolving on the Kelvin-Helmholtz timescale, and infer from that an age for your pre-stellar cores. Broadly, denser cores have lifetimes close to the free-fall time, which might imply that they evolved from sub to supercriticality. We can also use astrochemical models. Many chemical clocks give lifetimes for cores of a few hundred megayears, so a few times the free-fall time, but shorter than the amber-polar diffusion timescale, although there are exceptions. One exciting thing that might clear this up is being able to actually make better measurements of the magnetic field strengths in these objects using H1 and self-absorption Zeeman measurements. We have one measurement of this so far in a particularly isolated pre-stellar core. It'd be interesting to see where this goes when sample sizes get larger. And finally, I've so far talked entirely about low-mass cores, which is mostly because high-mass cores are complicated. High-mass pre-stellar core candidates, we're still looking to see whether they exist. The candidates that we have are typically identified through Jeans mass arguments, implicitly requiring large magnetic fields, and there are still a few candidates. Conversely, ALMA observations of high-mass star-forming regions have shown these very magnetically supercritical looking geometries, toroidal and suggestive dynamics dominated by gravity and rotation. So the picture remains hazy here. Broadly speaking, currently observations suggest that low-mass cores are probably evolving in a state somewhere near magnetic criticality. High-mass cores we still don't know, but possibly slightly more supercritical. And I'll hand back to Mehrnoosh now. Thank you.
Thank you, Kate. So now putting all the magnetic field studies together so far, for the geometry of magnetic fields in cloud to filament to core scales, we see that perpendicular or parallel magnetic fields are dominant depending on the density, and in 3D, arc-shaped magnetic field morphology has been observed for some regions. For filament scales, the same perpendicular and parallel, depending on the density, is observed, and a transition back to parallel is also observed, depending on the density or at the location where the filaments are merging to a hub system. For cores, as Kate mentioned, magnetic fields tend to be parallel to the minor axis of cores for starless cores, and to be hourglass morphology for high massive cores. When comparing the energy balances in the cloud scale, the system tends to be subalphanic, subcritical. For filament scales, sub, super, transalphanic, and criticality have been observed. For cores, low mass cores, the system tend to be transalphanic and transcritical, and for high mass cores, they're superalphanic and supercritical so far. And in all these scales, the magnetic fields seem to reduce the star formation efficiency. Now, we'll need a lot more observations to quantify these better. And there are exciting new observations coming up with new instruments. For example, NICA-2 on IRAM telescope, AMKID on APEX, Toltec on LMT, and Fred Young submillimeter telescope, particularly the PrimeCam instrument. And these will make dust emission possible, observations in many regions possible. For dust extinction, the recent data release of GPEPs and the upcoming data of Pasiphae will, in near infrared and optical, will enable us to improve the precision and accuracy of magnetic field observations. For Faraday rotation, the square kilometer array and its pathfinders, for example, ASCAP, LOFAR, NGVLA, and the upgrades in this Dominion Radio Astrophysical Observatory will make further progress. And for Zeeman measurements, ALMA, FAST, SKA, and NGVLA can be used. We've made significant progress in simulations as well. For example, the zoom-in approach to molecular clouds from kiloparsec scales, and also inclusion of cosmic ray and models that track chemical evolution in the system, when further progress in these regions is expected in the next few years. So we've posed 4 main questions for the next few years. One is how the cloud scale magnetic fields connect to the larger scale and the cold neutral medium, and how do they evolve in time? Is there critical density at which the systems become gravitationally unstable, and is there a relation between this density to HRO transition? And then is there observational evidence between correlations of magnetic field and the magnetic field metrics? And finally, do magnetic fields play a different role in low mass stars than high mass stars? So in summary, we've made significant progress in the past few years. Finally, after decades of work, we are emerging to a qualitative understanding of the role of magnetic field in star formation. And it would be really interesting to start quantify this in the next few years. Magnetic fields connect the gas from large-scale cloud to low-scale star-forming regions, and magnetic fields play a role in star formation through different instabilities. So finally, there are a few exciting posters on magnetic fields. Sorry if I've missed your poster, but please make sure to visit these posters if you'd like to know more about magnetic fields. Thank you.
Okay, thanks so much. So this chapter is open for questions. So from here, yes.
Hi, Mordecai Maklow, American Museum of Natural History. I would just like to emphasize, and this is maybe to Kate's points particularly, that Nakano, back in 1998 here in Kyoto, made the very important point that an MHD-supported cloud evolving by ambipolar diffusion has a column density so low that you can't detect it against the background. So any core that we detect is already dynamically collapsing. So I think we need to be careful about how to interpret the field geometries in observed cores, because they're all collapsing already.
Yes, I agree entirely. The thing that really struck us when we were putting this compilation together, everything we know about dense cores, is how contradictory all the information is. If non-ideal MHD effects are important anywhere, I would guess it would probably be in these environments, but
Disks.
in disks. Sorry, discs are not our problem. Discs are next talk's problem. But yes, I agree. Thank you.
The next. So please state your name and affiliations.
Sure. So I'm Zipeng Hu from Australian National University. So I'm always wondering about using the mass to flux ratio to talk about the energy balance across the clouds. Because if we are using Zeeman effect observation results, then normally the beam size is pretty small and using a really local information in a small region and to quantify the whole cloud. If we are using the DCF method, then you are always comparing the column density with B field. But column density is along line of sight, and the B field is from the plane of sky scenes. So you have to assume the plane of sky B field is almost equivalent with the line of sight components. So I think there's a lot of uncertainty here, and so I think that energy balance ratio is not that clear to me through the mass to flux ratio.
Yes, that's a great point. So one thing that we emphasized in the chapter is also that we are probing line of sight magnetic field with Zeeman or plane of sky magnetic field, and with mass to flux ratio we need to get 3D magnetic fields exactly, and column density is its integration along the line of sight. So there are all these uncertainties, and for the mass to flux ratio of Crutcher et al. 2010 as well, there has been studies emphasizing the importance of including the uncertainties in column density and in magnetic field. So that's a very valid point, and yeah, we need very accurate observations to further quantify this in the next few years.
Right, thank you.
Okay, the back side.
Riwas Pokhrel, University of Toledo. My question is, you mentioned about using Faraday rotation for estimating magnetic fields in molecular clouds. I was wondering if there's some comparison with other techniques, with the Faraday technique, especially in the denser region of the clouds where DCF technique is a little bit dicey. And do you have any idea of like which one would do a better job, especially in the denser region of the clouds?
So for Faraday rotation, this technique, for like very dense regions of molecular cloud that we are in the dominant by molecular gas and molecular regions, we compared them with Zeeman observations. And in terms of strength and direction, they're consistent with Zeeman observations. For the envelopes of the clouds, we compared them with atomic Zeeman observations, particularly for Orion A, where the same reversal have been observed by Zeeman measurements by Hylas, and the same orientation of reversal is seen. For the very dense regions, if you want to probe like very localized regions, the best technique would be Zeeman measurements, which provides the line of sight component. But probably comparing all these techniques together and, for example, considering the systematic biases would also help us in our studies.
Yeah, thank you.
Okay, from back.
Hi, nice talk. Daniel Seifried from the University of Cologne. You mentioned magnetic fields reduce the star formation efficiency, and I was wondering, is it really like this, or is it more the indirect effect that they slow it down such that actually feedback, as Mark yesterday showed, has enough time to disperse the cloud?
So in the studies that I remember off the top of my head, they have been indirect. And also like combining, for example, feedback with magnetic fields, they can further reduce the star formation efficiency. I don't know if Kate has something else to say.
I certainly think it's an important thing, an important prediction of simulations that we need to be able to test observationally, that the proposed coupling between magnetic fields and outflows, which essentially produces a multiplicative effect in decreasing star formation efficiency than either has alone. It's prediction out of a number of models now, and it's something we need to test with observations somehow.
Mark Krumholz, Australian National University. Can you go back to your slide where you are comparing DCF and Zeeman? And while you're going, I'll just say my concern. You said, well, the trends are the same, but there's a factor of 3 to 5 systematic offset, and that's not so bad. But I'm worried that a factor of 3 to 5 is a lot here, right? Because if I took all of your DCF points and just moved them up by a factor of 3 to 5, all of a sudden I'd conclude the alphane Mach numbers are bigger than 1, or at least comparable to 1, and everything is magnetically supercritical. So if there's a 3 to 5 fact, right, should I be very worried, or at least am I wrong to be very worried, that a factor of 3 to 5 completely changes the interpretation as to whether molecular clouds are sub or supercritical and whether they are sub or superalphanic, right? If I believe Zeeman, they're all supercritical and superalphanic. So am I missing something?
Yeah. So these are the DCF that, so they haven't been corrected for the like 3 to 5 ratio here. They're the DCF measurements as compiled from the studies. But no, so one of the things that need to be considered is, yeah, like the 3D magnetic field that some studies don't also consider when, for example, like comparing alpha Mach number or, for example, like mass to flux ratio. So we need to quantify this further to like the table that I showed at the end, that's the system of subalphanic or superalphanic. We need to have a lot more precise observations to quantify further.
But just to be specific, am I correct in thinking based on what you've said that if I believe the Zeeman measurements more than the DCF ones, I should think molecular clouds are supercritical and superalphanic? If I believe Zeeman more than DCF. Okay.
I would say so. However, it is worth bearing in mind that the Zeeman, on average, provides you half of the line of sight magnetic field strength. So they themselves, like the line of sight magnetic field strength by itself is not necessarily enough to determine the full strength of magnetic field. With the factor of 3 to 5 thing, I would say anybody using DCF should be worried. And I say this as someone who uses it myself all the time. It's a back of the envelope calculation that we're still using from the 1950s that we're still using today. I think, if anything, this is a sort of cautionary tale. It works better than it's got any right to, but it's clearly got systematic biases in it that we don't yet fully have a handle on. And frankly, the data in the last few years has got so good that we are scrambling to catch up with our ability to use this kind of method to interpret it. So when we were writing the chapter, we did a quick straw poll at the end as to who believed DCF more or less after having done all of this compilation. And I think 2 people believed it more than they did before, 2 people believed it less than they did before, and 1 person still didn't know. So I think our conclusion on DCF was it works better than it's got any right to, but if you're using it, you need to know that it's probably an overestimate still, despite all our best efforts.
Yeah. Okay, 3 minutes remain.
Yes, just a brief comments. One about the future observations of Zeeman with ALMA. You know that ALMA is quite not very good for Zeeman because the restrictions are very high. So specifically to detect the Zeeman splitting is going to be very difficult. And the problem is ALMA is not going to do anything unless the community makes them to really improve the Zeeman observation, the circular polarization. So that's one thing. The other thing is about superalphanic motions at the core scales. Here, just I want to comment that in the line width, we may have a significant contribution from gravitationally dominated motions and not turbulence. So when you do these estimations at the core scales, especially between 1,000 and 2,000 AUs or less, maybe there you're dominated by gravity, not by turbulence. Okay.
To mention about Zeeman, yeah, so especially the off-axis feeds really introduce uncertainty in Zeeman measurements. But looking at absorption lines from Zeeman and further quantifying it through for simulations may enable us to use also like ALMA better for Zeeman measurements. For the cores, do you have?
Yes, I agree entirely that we need to understand, firstly, what our line width is actually measuring when we use it, and secondly, alpha Mach number we can be referring either to bulk inflow or to turbulent motions. You need to know which one you think you're talking about when you do this kind of analysis.
Okay, so this is a final question.
Okay, so I'm Adam Ginsberg from the University of Florida. Kate, you pointed out in your brief component that the presence of an hourglass was an indication of a magnetic field that used to be important. But can we say anything from the lack of hourglass morphologies in a wide range of sources? Are we able to say that there are some where the dynamical field was never, or the magnetic field was never important?
It's an interesting question, and it's something I don't have necessarily much of an answer to at the moment. It's something that was very interesting. Shame we didn't really have time to show all of the ALMA results because they are incredible. Quite a lot of low-mass cores show magnetic fields that bear absolutely no resemblance to an hourglass whatsoever. The problem is that, especially with ALMA, all of those objects already have embedded protostars. And very often what we seem to be seeing is dust in outflow cavity walls and magnetic fields that have really significantly been reshaped by protostellar outflows. So it's very hard at that stage to say whether you're seeing the remnants of a magnetic field that was dynamically irrelevant as the thing collapsed and just got dragged around, or whether you're seeing magnetic fields that have been moved post-star formation. So I think we really need more and better observations of starless cores, and I think here the H1 in self-absorption really might, because the interesting thing with L1544, sorry I skipped past it because of the time, is that we measure there what is measured there is a supercritical mass to flux ratio even in the envelope of the core, which would suggest that that is a dynamically irrelevant magnetic field from the get-go. However, that's one observation of a very isolated source, so we do need to find out whether that's the exception or the rule.
Okay, thank you so much. So let's thank both speakers again.